All right, we are now recording. Let's get the current slide up here, and we will go from here. Now, before we go any further, though, someone in my last class told me something that I had never heard before, and I wanted you to know it too. Now, I'll give a little caveat to it, but I think it'll still be okay. You remember I've been telling you how this book has LarsonPrecalculus.com and CalcChat.com. Okay? The new edition also has a new one called CalcView.com. You don't have that for this book. However, the student told me that now they have an app you can get for the CalcChat.com. And since y'all have CalcChat.com, even though that app may be, I don't know if it's only for the new edition, as I've told you before, hardly anything changes between the editions. So I bet you the vast majority of the problems you'll be able to view on CalcChat.com via an app if you don't want to have to be sitting down at a computer. So I did not know that before this morning, so take advantage of that if you. Yeah. All right. Now we were getting ready to start example 7. The reason example 5's up here is 6 and 7 weren't on the slide set. So we were doing the examples on this one, and so let's go from there. First, I want to know any questions from anything we've done so far. Any?
I have a question.
Yeah.
Okay.
All right, has nothing to do with trig.
No, it was with some of the homework problems.
Oh, homework.
Yes.
Yeah. I'll be glad to do any of those anytime.
I'll ask you go over this.
Okay. All right. All right. Here's example 7. Okay. The blades of a wind turbine are 116 feet long. Have any of you actually seen a wind turbine? I know you've probably seen pictures of it. Have you actually seen those? When my wife had professional meetings out in Utah the week between terms, between summer and fall, so we went out early and drove around and went to a place, Twin Falls in Idaho. We saw Shoshone Falls, which are called the Niagara of the West. They were really pretty. The Snake River is just fascinating, the history of that. We drove over to Wyoming, and we visited Jackson Hole and Tetons and Yellowstone for a day. Please, if you ever have an opportunity, go to Yellowstone. It's just incredible, the geology that's there. It's like no other place on the planet. It's really incredible. So we had a good trip there. But when we were driving through, and then later we drove then from Wyoming back to Utah, Salt Lake City. It sounds like a lot of driving, but all that is in a pretty relatively small region. Just we went to 3 different states. But in Idaho, in a little bit in Wyoming, and in Utah, there were several places you just saw these wind farms, these turbines out there spinning. And thought, way to go, cheap, clean energy. Okay? So, these wind turbines, it says, the blades of a wind turbine are 116 feet long. Okay, I'm going to try to draw a wind turbine. My drawing stinks. Way high off the ground here, because you don't want, you don't want to be chopping any trees or cattle or people on tractors. And then the wind turbine blades are like this, and the length of the blade is 116 feet long. Okay? The propeller rotates at 15 revolutions per minute. 15 REV per MIN. Now I'm writing it that way. I don't write it very well. Revolutions per minute. But most of the time we call that 15 RPM. If you ever see that, that stands for revolutions per minute, RPM. I wrote it that way for you. Okay? 15 revolutions per minute. Okay? Find the angular speed of the propeller in radians per minute. Now, do you remember what symbol we use to represent angular speed? Anyone remember?
Angular speed isn't it sum over t? T is time.
Okay, yeah, that's exactly what it is. Angular speed, it would be angle per, it's really radians per second, except they're asking per minute. Okay, so what an angular speed, but what I was asking for, what's the symbol for it? Does anyone remember? Here's sort of a hint. Angles, except in some circumstances we use capital letters for angles, but most of the time we use the Greek symbols for letters. The favorite of everybody to state it. Yeah. What's that? Yes, it's the lowercase omega. So omega is, that's what we're looking for. The angular speed per minute, this is the unknown. That's what we're looking for. And that will be measured in, now notice here, I'm starting you with the units. It's measured in radians per minute. That's what it's asking for. Find the angular speed in radians per minute. Now, that's the key to this problem. There really is not that much trig involved with it, except you're dealing with angles. But if you look at this, and you see you're starting out with 15 revolutions per minute, so let's start there. 15 revolutions per minute. We're going to multiply this by blank blank, and we're trying to get radians per minute. Okay, now I'm doing this strictly with units, not doing any formulas or anything, but just using units. Now, you tell me, what does it look like? And remember, always put the units. This is the place for our numbers. This is the place for our units. Always put the units in their place. What do we need to put here so they can go from revolutions per minute to radians per minute? Okay, wait. Okay, you're getting me numbers. I want just units. And we're not doing a conversion from degrees to radians. I want just units. Here we have revolutions per minute. We need to multiply by something to give us radians per minute. Now, what did we lose going from here to there? Revolution. So how can we lose that? Where would we put it? Put it in on the bottom, exactly. If we put revolutions down here, okay, and what do we need to put on the top? We got minutes where we want it. Radians, okay. So now the question is, here's the question, how many radians are in one revolution? Yes, exactly. So you just multiply this by 2 pi radians per one revolution. Or it could have been how many revolutions per radian, but this is the easy one. So guess what our radians per minute is? Which will be our omega. Multiply. Numerators. 15 times 2 pi. Not that hard of math. 30 pi radians per minute. Multiply the denominators. 1 times 1 is 1. So there's your answer. Yes?
We didn't do nothing with the 116 feet. We didn't do nothing.
Not yet. Absolutely. Okay, now here's another issue. It's a very good one. Glad you brought it out. Okay? Sometimes students impose this rule on problems. The rule being the conservation of data. If they give you something in the problem, you better find some way to use it. No, not necessarily. I can remember when I first started, I've always tutored and done some substitute teaching and other things like this. But when I first started in the 2-year college system, I'd been working at Southern Research Institute as a research physicist there in a radon study. But then the government cut off all external or extramural funding, so we didn't have any funding anymore, so they had to let the whole group of us, there were like 6 or 8 of us in that group, had to let us go because there was no funding. So that year, I was just doing whatever I could, so I signed on at Jeff State and was an adjunct math instructor there, teaching 090 and 098. I think it was only 090. And I can remember one of those problems in the text. It said, you can buy a box of 24 cookies for $1.19. How much would 3 boxes cost? Okay? Pretty simple problem, right? Except for those students who use the conservation of data in a problem, and they said, you got to use that 24 cookies somewhere. So some of them multiplied by 24, and some of them divided by 24. So some of them had those 3 boxes of cookies costing hundreds of dollars, and others of them had them costing 3 or 4 cents. Okay? Because whether you multiply by 24 or divided by 24. But guess what? You're buying 3 boxes of cookies for $1.19 a box. That's $3 and something for the thing. Not 50 or 60 and not 12 cents. Didn't make any sense to do it 12 cents. 3 boxes of cookies cost you less than 1 box? No, because they gave you the number you got to multiply or divide by or do something with it. Okay? No, you don't. So no, we didn't use the 116 here at all. We are not using conservation of information in the problem. Okay. So, but we did answer that question. That was the A part. The B part, however, says find the linear speed of the tips of the blade. So here's the tip of the blade. How fast is it traveling? That's the linear speed. The angular speed was what we got here, 30 revolutions per minute. So how fast is that? Guess what? Now we're going to use the 116 feet. Okay? So, how do we do that? Any ideas? All right. Now we had a couple of formulas on the previous page, and here was one. The linear speed v is equal to arc length over time, s over t. Okay? So, now, what we have to do is get arc length. And do you remember what arc length was? And while we're at it, let me go on and write this, though we didn't use it. This is theta over time. Theta being the angle subtended over time. Omega, angular speed is angle per unit time, and linear speed is length per unit. Okay? Now, the one they didn't give you, okay, would be, what? You tell me, what is S? You knew that from an earlier one.
It's radius times theta.
Exactly. So this is r theta over time, right? Well, theta over time is your omega. Okay? Let me get your name, please. Kelsey? Chelsea, I mean, that's what I meant to say. Yeah, there you are. Williams, right? Last name Williams? Yeah, okay. Good deal. All right. I've got Chelsea's in 3 of my classes, so I'm make sure I got that right. Okay. This theta over t, that's exactly what your omega is, right? So guess what we do? We multiply that answer by r. Yes, your r. So this would be 116 times 30 pi. Okay? And by the way, the 116 is in feet, and 30 pi is radians per minute. So this is going to be, and radians, remember, is not really a unit, it's just a ratio. So really, this is per minute, is what we call it. We put radians there, but there's no, it's not a unit, really. So this will give you the speed in feet per minute. All right. If you multiply that out, that would be a 0, an 18, a 4, and a 3 pi. So it would be 3,480 pi feet per minute. Guess what? That's going pretty fast. Remember, pi is a little over 3, so that's going to be going close to 10,000. Okay.
So when we leave our answer, we just leave in pi.
You can leave it in pi, or if you want to, if you want to multiply it out and approximate it, you can do that. What they did in the book, they wrote an approximate answer, so they did multiply by pi. You don't have to. I can figure it out, but you know, someone use a calculator and tell me what you get. $3,480 times pi. $10,933, is that what you said? That would be feet per minute. Okay, now frankly, when I hear this, that it's going at 15 revolutions per minute, that's 4 revolutions. Wait, is that right? Yeah. A minute is 60 seconds, so that would be 4 revolutions a second. That's going pretty fast, but not super fast. 4 revolutions in a second. But with that blade that long, look how fast it's going. I don't want to be standing under here and get my head on, okay? Miss me, okay? That would be pretty fast. Most of the time, they don't turn anywhere close to that fast, okay? Even 4 revolutions a minute. Wait, 4 revolutions a minute is pretty, no, 4 revolutions a second, 15 revolutions a minute, okay. All right. No, that's 1 revolution every 4 seconds. I don't know what I was saying. Okay. Anyway, that's the answer. All right. This was the example 5. We just did 7. But now we're moving to sectors. A sector of a circle is the region, now I'm going to use a different one, area bounded by 2 radii of the circle and the intercepted arc. Okay? So if this is a circle, good circle, there's the center, and you're going to do the region or the area of that circle bounded by this radius and that radius, swept across here by that angle theta. That's the area, the sector is the area or the region of that circle. Okay? So there should be a formula for that, right? Here's what it is. The area of a sector of a circle of radius r, the area A of that sector with central angle theta is 1/2 r squared theta. Now, yes.
Can you go back real quick? It's bounded by 2 what?
Second, radii. Yeah. In other words, this radius to that radius. The area of the region in there is called the sector. Okay? Now, 1/2, A is 1/2 r squared theta. Let me give you a few hints I don't memorize well, so I like to use things to remember. Okay, area are measured in square length units. Well, theta is measured in radians, which is a ratio. It has no units. Okay? But radius is measured in length, and length times length is area. Okay? So you got to have an r squared in there. Now, what does that almost look like? An area that's 1/2 something another squared times something another. That looks like a triangle, doesn't it? 1/2 base times the height. Well, let's see if that would be helpful to us. Let's go back here again. And let's imagine that almost looks a little bit like a triangle, doesn't it? Okay? So if we did 1/2, the base, that base would be R, right? Okay. Now, what would you call the height? Well, it's not quite the height, but let's use instead of height, the arc length, S. And what is R theta. So R squared theta. Look at that. Now, that doesn't substitute for height, but that helps me remember it. Okay? 1/2 R squared theta. Okay? But frankly, if you were working for me, and we had a business and we were doing something, do I want you memorizing formulas, remembering? Oh, I think I remember. I think it was something like this. No, I want you looking it up. So I want you to make sure you've got the right formula. Okay? Let me get your name, please. Doc. Yeah, Doc. I wasn't paying attention. I knew it was you. There you are. All right. Good deal. So there's the area of a sector of a circle. And by the way, what's theta measured in? Say again? Radians always. Okay? All these formulas are based on S is equal to R theta, only on radians. So let's do example 8. Oh, they don't do example 8. Shame on them. Let's do example 8 now. You got it in your book. You can look at it. A sprinkler on a golf course fairway sprays water over a distance of 70 feet. So here's a sprinkler, and it sprays at 70 feet. Big, strong sprinkler. Okay? Through an angle of 120 degrees. Something like this, 120 degrees. Okay? Find the area of this fairway watered by that sprinkler. What is the area of that? What's your formula? Oh man, I have trouble remembering that, don't I? All right, what is it? 1/2 R squared theta. Okay? Guess what your R is? 70 feet. Guess what your theta is? 120 degrees. So is it plug and chug time? What is it? 1/2 and it's the joint, right? Okay. 1/2. Anyone know what 70 squared is? Sure you do. 4,900. Square the 7 and double the number of zeros. Okay? And that would be feet squared, by the way. And what's our theta? Oh, really? This is a big area. Why? Yeah, you can only use radians, so you have to convert. So what will your theta be? 120 degrees times blank blank is equal to blank radians. Now we can go back to what you were trying to do before. What do we put where? Yeah, radians on top. I can't write. Okay, and degrees on the bottom. Now give me the ratio that matches radians to degrees. Pi radians is 180 degrees. Okay, now I can wipe out my zeros there, and I know 6 will go into 12 twice. 6 will go into 18 3 times. So that'll be 2/3 pi radians, right? 2 pi over 3 radians. That's what we put in here. Times 2 pi thirds. Well, this 2 and that 2 cancel out or divide away. And that leaves me 4,900 pi over 3. Now, 3 won't go into 4,900, but the answer is going to be in square feet. So someone with their handy-dandy calculator, because I bet you the owner of that golf course is probably not interested in how many pies of an area. He wants to know how much of the golf course he got covered in square feet. Do that calculation. 4,900 times pi divided by 3. It's going to be awfully close to 4,900. Probably no more than 5,000 or not much more, is it? A little bit more. Because you see, pi is very close to 3. So these almost don't cancel out. It'll be a little bit more up here. And multiply that with 4,900, you get something. What you get? 5,131. Yeah. 5,131. Is that what you said? Square feet? Huh? Yeah. Square feet. All right. Now, really, that's more precision than you get because they only gave you this with most 2 significant digits. This is at most 3. So your answer really, I would say 5,100 square feet. Approximately. 5,131 may be closer to what it is, or it may not. I mean, you just don't know. We don't have that many significant digits. But you get the general idea. Okay. Guess what? They do have a checkpoint. Those are on LarsonPrecalculus.com. I don't think they have an app for that one. I think they only have it for CalcChat.com. But that's what your homework exercises are under. So let's do the vocabulary. Top of page 269. 2 angles that have the same initial sides and the same terminal sides are said to be blank. Coterminal. Excellent. Okay? Let me get your name, please. Jeremy. Got it. There you are. We're just missing Taiwan and Justin. Oh, and by the way, I'm sorry. I apologize. Usually when someone new comes in, let me, yeah, do you have a question? Or you just, oh, yeah. Okay. 51,000? Okay. Did you type in 4900 or 49000? Yeah, I think it's on. Now, sorry, I meant to say this earlier when I found out it was your first day here. Okay, everything we've done so far is out there on YouTube. Okay, I record, that's what the screencast-o-matic at the beginning of class. I record everything that we do, what I say, and what's projected on the board. Now, my pointing the hands, that doesn't get recorded. Just what projected on the board and thing. So you can go back and hear the first day of class, we did mostly the syllabus. Did we get to research paper, my locator card? That probably went into the second day of class. Locator card, and that kind of stuff. And then we started in 4.1. And everything we've done up to now, you can see. This is a 4th class now. So there's 3 before today. So you can go back and view any of those. And I go over the syllabus and everything in that, so you can go see that. Now, on that subject, hopefully tomorrow, I'll be able to get some things done for the class. So far, every time I've had office hours, I've had something else that came into play. Registering students, changing classes, canceling classes, doing all this kind of stuff at the first of the term. And yesterday I had 2 hours of office hours. I was hoping to get stuff done. One of my instructors on the math department chair, one of them's printer was on the way out. She had to bang on it, hit on it, do things to it, and sometimes it prints and sometimes it doesn't. So she needed a new printer. So I asked our IT people to find me the company that we order from and get a quote. They're happy with it. So I got that, so I had to do requisition yesterday. But guess what? At the same time, my printer, the cartridge, the toner is almost gone. And so I had to order more of that. We have a company that does it, but they don't cover my printer. It's too old. I'm too old. Well, never mind. We won't go there. But anyway, so I had to order that. So she got me a quote, but it was for the wrong one. When I looked at it, I said, this isn't my printer. She said, oh, so she went back and got a different quote, and I did another one, and then she found a cheaper quote, so I did a third one. So that took my 2 hours yesterday, that and other things. I had phone calls or other things coming in. So far I haven't gotten this course done. I don't know what's going to happen tomorrow. Hopefully we can get by without anything major happening, and I can get some of the blackboards set up. Now, in between then, my physical science class, this is a mini-term class. We've already had one lab and one test, 20 people in the class, so I've got 20 labs to grade, 20 tests to grade, and we're having another lab and test today. So I hope to have all this done before I had to start grading mini-term classes. They start already. So anyway, it may not happen tomorrow. Hopefully it'll happen over the weekend. But I'll do the best I can. All right, we did vocabulary of the first question. Number 2, one blank is the measure of a central angle that intercepts an arc equal to the radius of that circle. What's that a measure of? 1 radian. That's exactly 1 radian. Okay? Number 3. This is on page 269, top of the page. Number 3. 2 positive angles that have a sum of pi halves are called complementary angles. Very good. Whereas 2 positive angles that have a sum of pi are called supplementary angles. Very good. Number 4. The angle measure that is equivalent to the rotation of 1/360th of a complete revolution about an angle's vertex is 1. Say again? Say again? Okay, 1/360th of a revolution. That would be 1 degree. Okay. How many times did I have to do that, huh? That's a degree symbol. Do you see it? Okay, never mind. All right. All right. Number 5. The blank speed of a particle is the ratio of the arc length to the time traveled. The blank speed of a particle is a ratio of the arc length to the time traveled. Arc length is a length, so that would be linear speed. And the blank speed of a particle is a ratio of the central angle to the time travel. Angular speed, you got it. The linear speed would be measured in meters per second, centimeters per second, feet per second, something like that, whereas the angular speed is measured in, say again? Angles per second, which what do we measure angles in? Radians per second. Very good. Don't do degrees. Okay. Now, the number 6, the area A of a sector of a circle with radius r and central angle theta, where theta is measured in radians, is given by the formula. Say again? You got it. All right, I would say bingo, but this is Alabama. We can't say bingo. Okay, come on. All right. Homework exercises. I've assigned some of these before, but I'll catch them again. Either 7 or 9 or both. This is page 269 and following. Okay? It goes through 271. Okay? 7 or 9 or both. Do number 11, it has 2 parts. Do number 13, it has 2 parts. Do number 15, it has 2 parts. Do either 17 or 19, 2 parts each. Do either 21 or 23. Do 25, it has 2 parts. Do 27, it has 2 parts. Do 29, it has 2 parts. And do either 31 or 33, they both each have 2 parts. Do 35, it has 2 parts. Do 37, it has 2 parts. Do either 39 or 41, or both. Do either 43 or 45, or both. Do 47. It has two parts. Now, did any of you try that at home? 47. You couldn't? Okay. We didn't have one like that in the class. That's why I stopped to ask. You want to do that now? 47A. If anyone knows what it is, you can guide me through it, okay? 47A says, in these exercises, convert each angle measure to a decimal degree form without using a calculator. Then check your results with a calculator. And here, this is page 270. And this is 4.1 exercise. And this is number 47. You want me to do A or B, or does it matter? Say again? Okay, name one of them. A. Okay? He likes A's. Okay, I'll remember that. Okay. Now, 54 degrees and 45 minutes. 54 degrees, 45 minutes. It said convert that to decimal degree form. We haven't talked about that. What do you think that would mean?
Just like, isn't it like degrees, minutes, and something?
Say that again.
Degrees, minutes, and seconds. You know what that means? Degrees, minutes, and seconds.
Okay, that's what we're in now, degrees, minutes, and seconds. Yeah. It wants it in decimal form, decimal degrees. Okay. What are decimals sort of related to when you learn? Say again? Fractions. Okay, let's write that as a fraction. That would be 54, and how many minutes are in a degree? Anyone remember? Remember the Sumerians? 60. Okay. So this 45 minutes would be 45/60th of a degree, wouldn't it? Because 45 minutes, it's sort of like on a clock. 45 minutes is what part of an hour? Okay. It'd be 45/60. I was looking for a number there. Let's reduce that, 45/60. What will go, say again? 9/12. Does that reduce any further? 3/4. That's what I was looking for. Isn't 45 minutes 3/4 of an hour? Yeah, you knew that. Okay. Now let's write that as a decimal. You got it as 54 3/4 degrees. That would be 54, say again, 0.75 degrees. That's what they're looking for there.
Okay, so you just basically, you just times 54, 3/4, right?
Yeah.
Right.
It's 54 plus 45/60th. 54 degrees plus 45/60th of a degree, which is 3/4 of a degree.
Okay. Yeah. So you add those together.
Yeah. Yeah. So something between 54 and 55 degrees, right? 45 minutes is in between. So it'd be 54.75 degrees. Okay. Now how about 49? Now they want it in degree, minute, second form. Did y'all do that one? Is that easier to do? Oh, sure it is. Okay. So you want to do 49A or B? Let's see. Let me write it somewhere else. 49A. 49A. This time they gave you 240.6 degrees. Okay? Now, in degree, minute, second form, I can tell you the degree part. What would that be?
240.
240 degrees. Now, what we got to figure out is how many minutes is 6/10 of a degree. Second? 3/5 of a degree. Okay. How many minutes is that? Okay? How many minutes is in 1 degree? 60. So that would be 60 times 0.6, right? 6/10 of 60 would be, and this is minutes per degree, that would be 36, right? So that would be 240 minutes, 240 degrees, 36 minutes. 6/10 of a degree is 60 minutes, so 6/10 of 60 minutes is 36. Without a calculator, you can do that, right? Sure you can. 240 degrees, 36 minutes. 0 seconds. Y'all do the rest of them? Good. All right. Then so we did 47A and 49A. You do 47B and 49B. Then do 51, 53, 55, 57, and any of the odds between 59 and 69. Okay? Any of the odds between 59 and 69. What's that? I'd say I would do probably more than one. But yeah, I'd pick things that are of interest to you, or that might have something to do with your major. Maybe none of them would, but yeah, just pick one or more. Yeah, I'll let you choose.
So our test in this class would be like basically book based.
Basically what?
Book based, like our questions would come from the book.
Yeah, well, I get them from the same test bank of the people that wrote the book. Yeah. And they'll be take-home, so you can have your books do it. Y'all wanted those take-home tests, if I remember right. I don't know why you want those, but anyway, you got it. Now, there are also some questions here. I don't like true-false questions, but they're not bad to look at and think through. I won't ever ask you a true-false question on a test. They also have some think-about questions. Think through those, so you don't have to write them out. They do have one writing question. You don't have to write it, but think through it. All right. That then finishes the section. Any questions? All right. Let's move on to, finally, 4.2. PowerPoint is pretty slow. Yeah, 4.1 was a long section. 4.2 is sort of long, but hopefully not quite as bad. All right, PowerPoint takes a long time, though. Here we go. All right. Continuing with trigonometry, 4.2 is trigonometric functions using what we call the unit circle. What do we mean by a unit circle?
That's a whole circle with all the radians and degrees and all that.
Okay, yeah, it's got all those in it. But what makes it a unit circle? Is that a unit circle? Is that a unit circle? What makes a unit circle? Unit. Any of you ever played the card game Uno?
Yeah.
What is Uno? When did you call Uno? When you had one card left, it means one. So a unit circle is a circle with a radius of 1. That's what makes a unit circle. Okay? Now, if trigonometry is the study of triangles, why have we got unit circles here? That is a good question, but they relate to each other. So we'll do the unit circle first, and then the next section we'll come back and use triangles, right angle triangle trig, which is where it really began. Back when I took trig, we started with triangles and then applied it to unit circles. This book and most books change it now. First we'll identify a unit circle and describe its relationship to real numbers. Of course, it has a relationship to real numbers. We'll evaluate trigonometric functions using the unit circle. And we'll use domain and period to evaluate sine and cosine functions, and also use a calculator to evaluate general trigonometric functions. Okay? So let's start with the unit circle. Two historical perspectives of trigonometry incorporate different methods of introducing trigonometric functions. Traditionally, it was triangles, study of triangles. But one perspective is based on the unit circle. And the book likes this best, so it's doing it first. Now, if that circle has a radius of 1, can anyone give me an equation for that circle? Yes, the radius of that circle is 1. Can anyone give me the equation for that circle?
X squared plus Y squared.
Yes, the x squared plus y squared is equal to 1. That's why I was standing there. I was hoping you wouldn't read it on my shirt. Okay, now, that is true of every unit circle. If it's a circle of some other size, then you have to put r squared here. But if r is 1, 1 squared is 1. Okay. Now, they picked out 4 points on this circle. They're pretty obvious. They centered the circle at the origin, and I know that these 4 points are on the circle. 1, 0, that's a radius of 1. 0, 1, that's a radius of 1. 0 minus 1, the length of that radius is 1. And, I'm sorry, 1, negative 1, 0, and 0, negative 1, the length of that is 1. So I can pick up those 4 points. Can we name any other points? Like this one right here. Let's say that has an x value of x. Can you give me what the y value would be?
If you took the decimal, it would be nice.
Okay, you need that, but guess what? If I told you it was x, whatever that x was, by the way, x has to be between 0 and 1, right? Okay, let's say it's 1/2, okay? If we choose x of 1/2, then what's the y? Can you tell me what y would be? I guarantee you it's not 1/2. Say again? Square root of 3 over 2. How did she get that? You remembered it, okay? Okay, I'll show you how you could get it. If x was 1/2, okay, let me get my pen in place. So we're going to choose x equal 1/2. Now this equation here, what is 1/2 squared? No, 1/2 squared. 1 doubled is 1. 1/2 squared is 1/4. Plus y squared, that's what we're looking for, y, is equal to 1. What can we do from there? Yeah, subtract 1/4 from both sides. And that gives us, this goes to 0, y squared is equal to 1 minus 1/4. Oh my goodness. Okay, if you had $1 worth of quarters and you took 1/4 away, what would you have? 3/4, okay? That's pretty simple, isn't it? Okay? This would be 3/4, 3 over 4. Okay, go back to the fractions, folks. Okay, yes. And now we take a square root of y, and you get y is equal to the square root of 3 over, what's the square root of 4? 2. Okay, you got it. Almost. When you take the square root of both sides of an equation, this gives you y for sure, but this gives you plus or minus the square root. There's the plus square root of 3 over 2. There's the minus square root of 3 over 2. So x equal 1/2, you have 2 values here. Plus square root of 3 over 2, minus square root of 3 over 2. Plus or minus. Okay? So for any x between -1 and 1, any one, you can find the y. Or any y between minus 1 and 1, you can find the x. If you know the one, you can calculate the other. Right? Because you know every unit circle obeys that formula. Got it? Now, here's imaginary thing here. Imagine that we have a real number line. And for some reason, I know why, they start it at the end here and make it go up this way. Isn't where we usually draw a real number line, but let's just imagine we have. So a real number line going up, there's ticked off spaces there. Okay? And I'm thinking from what I'm looking at here, this is 1 unit here. I think this length and that length is the same. So here's a quarter, a half, 3/4, and 1. Remember that length is 1, right? If I'm going to take that real number line and bend it around the circle, I'm really strong, right? So I'm going to bend it around the circle. Okay? This is a real number here. It doesn't have to be there. It could have been here, here, anywhere there, or up here or here. Bending that number line around the circle, that gives me some number t. That's the length of the arc here, t. Okay? And by the way, we always keep our t positive. T is greater than 0. So we drew it up that way. Over here, your t is negative. And you're drawing it negative down, negative y. So that would be a negative t. Okay? Imagine wrapping the real number line around the circle with positive numbers corresponding to counterclockwise wrapping, negative numbers with a clockwise wrapping. Okay? As shown here. Okay? Now, what we're trying to do is relate this t to that x and y, maybe that angle. That's where we're heading. So just imagine we're wrapping the real number line around the circle. Okay? As the real number line wraps around the circle, each real number t corresponds to exactly one xy point on that circle. This t corresponds to that t corresponds to that to this one, this one to this one, this point in here to there. Every t value you have on this line corresponds to some point on that circle. Right? Okay. For example, the real number 0 corresponds to the point 1, 0. There it is. Numbers t equals 0, you're right there. It corresponds to this point 1, 0. Right? Some other t up here will correspond to this point 0, 1. Okay? This one corresponds to this point xy. This one will correspond to some other point xy. Okay? So every point on the real number line corresponds to exactly one point on the radius on the circumference of that circle. Okay? Moreover, because the unit circle, what is the circumference of the unit circle? All the way around the unit circle? 2 pi. Okay. That length would be 2 pi because this is the unit circle. Okay? That length would be exactly 2 pi. This would be pi halves. This would be 1 pi.
2 pi.
1/2 pi plus a pi is 3/2 pi. Okay? And that would be 2 pi. Yeah, we got it. Okay. So, moreover, because the unit circle has a circumference of 2 pi, unit circle radius 1, circumference 2 pi, the real number 2 pi corresponds also to that same point, 1, 0. So every real number corresponds to a single point, but some of those points correspond to more than one real number. And those on the unit circle will always be difference of 2 pi. Okay? 0, 2 pi. Okay. In general, each real number t corresponds to a central angle theta in standard position whose radian measure is t. No, t. Okay, whatever that t is, that's your radian measure t. So that's exactly what you're measuring. With that interpretation then of t, S is equal to r theta. We saw that before. This is arc length measured in t. If your r is 1, then theta and s are the same units. Theta is measured in radians, s is measured in whatever you're going to measure, and r is equal to 1. That indicates that the real number t is the directional length of the arc intercepted by the angle theta given in radians. Angle theta given in radians, the arc is measured in whatever you measure that. But they have the same values on that unit circle because r is equal to 1. Okay, so let's look at the trig functions then. From the preceding discussion, it follows that the coordinates x and y are two functions of that real value t. Okay? The xy value for every real number t, you get a specific xy value. So x is a function of t, y is a function of t. You can use those coordinates to define 6 trigonometric functions of t. The sine function, I don't like the way they do this. The sine, the cosine, the tangent, the cotangent, the secant, and the cosecant. That's how I like to think of them. I know why they put them this way, but I like to think of them the other way. Just get on all 6. These 6 trig functions are normally abbreviated by sine, cosine, secant, tangent, cotangent. But can we do cosecant that way? Why not? That's the same I already uses cosine. So how we abbreviate cosecant is leave out the vowels, CSC. Just use that. So that is why cosecant is CSC. All the rest of the first 3 letters. So even though this is a sine, it looks like sin, but it's not. So you can sin all you want to in 3 class. Okay. Now, here are the definitions of those trig functions. And just pulling them right out of the air and giving them to you. Now, this is only true of the unit circles. So let t be those real numbers, and they represent the angle, okay, in radians, and let xy be the point on the unit circle corresponding to that value t. The sine of t is always the y value. On the unit circle only now, okay? The cosine of t on the unit circle is the x value. The tangent of t on the unit circle is the ratio of y to x. But what's the problem there? X can't be 0 because you got it in the denominator now, so you have to exclude the places where x equals 0. Well, if you think about it, where is x equals 0?
It's right there.
X equals 0 certainly here, so that would be up here or down there. In the unit circle, these 2 points here do not have tangent values. Exclude the minus pi halves and pi halves, or pi halves and 3 halves. You cannot define tangent at those 2 points. Okay? The cosecant of t, and this is why they listed it right after sine, is 1 over y on the unit circle. Okay? But here now, y can't be 0. Well, I don't like doing them this way. I like to go to tangent and go down to cotangent. Cotangent is the reciprocal of tangent, which is x over y. But now, y can't be 0. And where would y be 0? Y is 0 here and here. See, there's a 0. Over here it would be minus 1 0. You have to exclude those 2 values for cotangent. Okay? Not defined at those 2. Okay? And then, just like cotangent is reciprocal of tangent, secant is reciprocal of cosine, and again, x can't be 0 just like it's been there. Those 2 values you exclude, and cosecant is reciprocal of sine. 1 over y, you have to exclude the y equals 0 like you did for cotangent, and that would be here. Those two values don't have the cotangent or cosecant. Now, I kind of don't like them introducing the unit circle first, because you get used to seeing this, and now you think that's going to be true from now on. This is only true with unit circles, okay? Any old circle, you can't use your XYs like this, but let me show you how you can use them, okay? Okay? We said on the unit circle, the sine of this angle is the y value. The cosine is the x value. The tangent is the ratio of y to x. The cotangent is the ratio of x to y. The secant is the ratio of 1. Where did the 1 come from? The radius. So let's back off for a moment. The sine is the ratio of y to radius. Y over 1, which is y. Cosine is x over 1, which is x. Tangent is y over x, ratio of those two. Cotangent x over y. Secant is radius over x, which is 1 over x, and cosecant is radius over y. So that's where those come from. I wish they would have thrown the radius in there, but then with the unit circle it's always 1, and that's why this is y over 1, x over 1. These two have nothing to do with the radius. This is radius over x, 1 over x, radius over 1 over 1 over 1. If you think that, later everything will make more sense. And that way you won't think, oh, the y value is a sine. It's the sine only on the unit circle, not on any other circle at all. Okay. Now, the definitions for the trig functions note that the tangent and secant are not defined when x is equal to 0. The cotangent and cosecant are not defined when y is equal to 0. For instance, because at t is equal to pi halves, guess what? Your x value is 0. So that corresponds to 0, 1. You cannot calculate the tangent there. You cannot calculate the secant there. Okay? Tangent of pi halves, secant of pi halves, undefined. You cannot do anything with it. Now, do y'all remember back from algebra when you had a place where the thing was undefined, when you were graphing that, what usually showed up there? Yes, but it was a vertical dot. We call them vertical asymptotes. You got it. And that's what you have for tangent, secant, and pi halves. You have vertical asymptotes. Similarly, the cotangent and cosecant are not defined when y is equal to 0, not x, but y. So therefore, you have vertical asymptotes at those at the values for which your y would be 0. Okay? So cotangent 0, cosecant 0, undefined vertical asymptotes. Okay. We'll get to that later when we're doing graphing as well. Okay, let me see if oh yeah. Now, this represents a unit circle, radius 1, divided into 8 equal arcs. Okay? The axes divided into 4 equal arcs. Now we're going to divide each one of those into by half. So you have 1, 2, 3, 4, 5, 6, 7, 8. So 8 equal arcs here. Okay? Now, the angles representing, or the t values of those arcs. Okay, now what is all the way around? 2 pi. Halfway around? Pi. Half of that? Pi halves, and half of that? Pi quarters, exactly. So this corresponds to 0, t equals 0, pi quarters, pi halves, 3/4 pi, pi, 5/4 pi, 3 halves pi, 7/4 pi, 2 pi, which is the same as 0. Right? Same coordinates as 0. All right. They threw threw some numbers on them. I knew what these were. This is 1, 0, 0, 1, negative 1, 0, 0, negative 1. How did they come up with those numbers?
Similar to the method we did earlier when we had got what was it? It was square 3 over 2.
Okay, that was, yeah. But that was when I went 1/2 here, and that went up here. So it's not going to be the same there. So we got to figure out why that wound up there. Okay? That's, okay. You tell me something here. This line right here, does it have a special name? Anyone remember what that line is called? The identity function. Why was that called the identity function? Didn't someone say that, or did I imagine? Did you say it? Identity function. What do we call it, identity function? Can you write that function for me? Yes, you can. I think you can.
Probably call it identity function because you can identify other functions.
Okay, not quite. Okay. How far out here, let's say I go out this far here, how far up will I go? Exactly the same. This line right here, what slope would you say that line has? 1. That means that line, and it goes through the origin, that line right there is y is equal to x, isn't it? Okay, y is equal to x. Now, can someone give me an equation that represents every point on that line, on that circle? Every point on that circle. Say again? X squared plus y squared is equal to 1. Yes, we remember that, don't we? Okay? Now, this may be what you're remembering from. Okay? Now, if y is equal to x, I can either plug in x for y or y for x. You choose. Which am I going to do?
Plug in x for y.
X for y. Okay, so that would be x squared plus, instead of y squared, I'll write. You said plug in x for y, so that would be y is equal to x, so I could plug in x squared again is equal to 1, right? Because y is equal to x, right? Can you solve that for me? 2x squared is equal to 1. Can you solve that for me? Divide both sides by 2. Okay? And that would give me x squared is equal to 1/2. And then what would we do? Take a square root of both sides. X is equal to, what would be better, right? Plus or minus 1 over root 2. Right? Remember, you have to do a plus or minus. Now, some people don't like writing a radical in the denominator. So how can you rationalize that denominator? Multiply the numerator and denominator by the square root of 2. Because what is square root of 2 over square root of 2? 1. When can you multiply by 1? Anytime you want to. Doesn't change the value, right? So what does this become? Plus or minus the square root of 2 over 2. Square root of 2 over 2 minus square root of 2 over 2. That's the y values. X value square root of 2 over 2 minus square root of 2 over 2. That's why they're the same. Because x is equal. Here x is equal to y. Here x is equal to y. Here x is equal to minus y. So that's why 1 is plus or 1 minus. But in the fourth quadrant, x is positive, y is negative. The second quadrant, the x is negative, the y is positive. That gives us those points. That has to be. There's no choice around. What t does that represent? Pi-fourths. T is equal to pi-fourths. Okay. Now, if that point here is on that t right there, what's the sign of this t? Sign of pi-fourths. The y guy. What's the cosine? The x value. What's the tangent? The ratio of this to that. What's the ratio of square root of 2 and square root of 2? 1. How about the cosine? Cotangent. 1, 2, because it's just flip them over. How about the secant? Okay, it'd be 1 over this. But let's go back. The x was 1 over root 2. If I flip that over, it's root 2. All right, so that would be root 2, and the cosecant would be root 2. Okay? We already know the trig function of that point in every one of those points, right? Because we know the xy values. It's a unit circle. We know the trig function values for every one of those. You think it's time to leave, don't you? All right, shame on you. Okay. Where do we get? All right, I think we beat that one to death. We'll start next time on the next unit circle down there, and that will be that one. Okay, let me give you a few more homework exercises. That wasn't enough. Okay, I think you can try to do 5 or 7. Maybe do 9 or 11. We'll stop there. Okay, wait, one more thing. There is sort of a good news, bad news situation coming up. The bad news is next Monday, there's no classes. I'm sorry, it's a holiday. Labor Day. The good news is it doesn't affect this class any because we meet on Tuesday, we don't lose the class. So good deal. We got it done. Okay.